We have examined vector addition, vector subtraction, and multiplication of a vector by a scalar. We now turn to a less straightforward question. What does it mean to multiply one vector by another? Consider two vectors of magnitude 3 and 5 pointing in different directions. Should the product be 15? Should it be more or less than 15? Should the magnitude, whatever it is, be assigned to a vector aligned with the 3 vector? Should it be assigned to the 5 vector? Should it be assigned to a new vector pointing in a third direction? Or should the product even be a vector? There is no obvious answer, and this fact alone tells us that there is an infinite number of possibilities of what it might mean to multiply one vector by another. Our interest will be confined to two vector multiplication operations. In section 2.4, we will examine something called the dot product, which is a multiplication operation between two vectors that yields a scalar. In section 2.5, we will examine something called the cross product, a multiplication operation between two vectors that yields a third vector related to but not aligned with the two multiplying vectors. Both operations have a physical interpretation we will find useful. The dot product is a multiplication operation between two vectors that is especially useful when one of the vectors is a physical quantity, for instance a force, and the second vector is a unit vector. In this case, the dot product produces the scalar magnitude of the force that acts in the direction of the unit vector. To provide some motivation for this, consider the problem shown in example 1. Here we have a truck driving alongside railroad tracks, pulling a locomotive. The chain connecting A to B carries 3,000 pounds, but not all of that goes into pulling the locomotive along the tracks. How much of that 3,000 pound force is directed along the tracks? The x-axis is directed along the tracks, so the I component of the force seems like the correct choice, and it is. From the figure, RBA, which is RA minus RB, is 14I minus 5J minus 2K feet. The magnitude of RBA, which we could get from the square root of the sum of the squares, turns out to be equal to 15 feet. The unit vector that points from B to A is RBA divided by its magnitude, and that turns out to be 14 over 15I minus 5 over 15J minus 2 over 15K. The force from B to A is equal to the tension on the unit vector from B to A, and that's 3,000 pounds times our unit vector 14 over 15I minus 5 over 15J minus 2 over 15K. The I component of the force is 14 over 15 times 3,000, which is 2,800 pounds, and that is in fact the amount of force that's going to pull the locomotive along the tracks. We will see shortly that the dot product between FBA and unit vector I will have the effect of extracting the scalar component multiplying I while discarding the remaining two components. This becomes important when neither the force nor the direction of interest is aligned with the coordinate system. Here we have a second example similar to the first, but with the coordinate system rotated 30 degrees about the z-axis of example 1. How much of the 3,000 pound force is now acting along the train tracks? Before answering this question, we will introduce the dot product, discuss its properties, and show how it can be used to extract useful information in three-dimensional problems. It is important to realize that we define the dot product this way. Given two vectors A and B, we define the dot product between A and B to be a scalar equal to the product of the magnitude of A, the magnitude of B, and the cosine of the angle between A and B when the two vectors are positioned tail to tail. The most positive value of the dot product occurs when the vectors are aligned, theta equals 0 and cosine theta equals 1. The most negative value of the dot product occurs when the vectors are pointing in opposite directions, theta equals 180 degrees and cosine theta equals minus 1. The dot product is 0 when the vectors A and B are perpendicular to each other. We can use the definition of the dot product to show that it also has these properties. The commutative law and the law of scalar multiplication are both straightforward. We could write A dot B from the definition is AB cosine theta. Because these are all scalar magnitudes, we could rearrange it as BA cosine theta, and that is in turn B dot A. We could do something similar with the law of scalar multiplication. Since our definition, in effect, gives us the multiplication of 4 scalar quantities, we can group these any way we like. To show that any of these permutations of scalar S multiplying A dot B are equivalent. The last law, the distributive law, is not quite so straightforward. So let's take a minute to convince ourselves that it really does follow from the definition of the dot product. Here we have sketched 3 vectors A, B, and C meant to be of arbitrary length and arbitrary orientation with respect to each other. We have the following 3 angles. We have theta as the angle between A and B, we have phi as the angle between B and C, and we have psi as the angle between the resultant B plus C and B. The definitions of A dot each of these quantities is given by these expressions. The question then is, does A dot R equal A dot B plus A dot C, where R is B plus C? To carry this out, we will make use of a couple of equivalent relationships involving right triangles. We can see the vertical blue line could be represented either as R sine psi, or equivalently it could be written as C sine of phi. In addition, the horizontal blue line could be written as R cosine psi, or it could be written as B plus C cosine phi. So keeping this in mind, we have our definition of A dot R, and we'll use a trigonometric expansion now to represent cosine of quantity theta minus psi in terms of the cosines and the sines of those individual angles. So A dot R is also equal to AR quantity cosine theta cosine psi plus sine theta sine psi. Now we'll use our equivalents in blue and write R cosine psi here in terms of B plus C cosine phi. So we'll end up with A cosine theta times B plus C cosine phi, and then we'll use R sine psi to write the second term as A sine theta times C sine phi. We'll pull AB cosine theta out of the first term, and then group together AC cosine phi cosine theta plus sine phi sine theta. And that second term then becomes AC cosine of phi minus theta. Now we can see from the definitions of A dot B and A dot C that those are exactly the terms that we have here. Therefore, it is the case that our dot product also obeys this distributive law, and we can use these three results, the commutative law, the law of scalar multiplication, and the distributive law, to get another expression for the dot product. Now consider the dot product between vectors with Cartesian representation. Because of the distributive law, we can reduce this to 9 binary dot product operations involving the unit vectors I, j, and k. Because the Cartesian system is mutually orthogonal, each of these dot product operations will yield either 0 or 1. We can see that any unit vector dotted with itself produces 1, since the operation yields the product of each vector magnitude, both 1, with the cosine of the angle between the vector and itself, also 1 since that angle is 0. The dot product of any unit vector with another unit vector not itself produces 0 in an orthogonal coordinate system, since the angle between the unit vector and the other unit vector is 90 degrees, and cosine of 90 degrees is 0. The result is that 6 of the 9 terms in the distributed dot product go to 0, and we are left with the sum of the product of the x, y, and z components of the two vectors. It is important to keep in mind the relationship between these two different expressions for the dot product. This expression, A dot B equals magnitude A, magnitude B times cosine theta, is a definition. A number of laws, including commutative and distributive law, follow from that definition, so that when A and B are written as decompositions in mutually orthogonal directions, it follows that A dot B is also equal to the sum of the products of the x, y, and z components. The equivalence of these two expressions means that we can find the angle between two vectors in three-dimensional space without having to identify the plane formed by those two vectors, let alone use geometry and trigonometry within that plane. The numerator in this expression is the sum of the products of the x, y, and z components, and the denominator is the product of each vector magnitude. More importantly, we can use the dot product to find the scalar magnitude of a vector entity acting along a particular direction if the first vector is the entity and the second vector is a unit vector. Here we have a plane defined by a force vector f and a unit vector aligned with the position vector r. Using the definition of the dot product, f dot u is the magnitude of the first vector times the magnitude of the second vector, which is just 1, times the cosine of the angle between the two vectors. If the unit vector is defined here, we can see from this right triangle that this definition gives us f parallel, that is, the scalar magnitude of f along the direction defined by the unit vector. The actual evaluation of f cosine theta comes about from using the Cartesian components of f in the unit vector, because we also know that this is fx ux plus fy uy plus fz uz, where f and u, x, y, and z are the individual Cartesian components of those two vectors. This quantity f dot u is a scalar quantity that we will call f parallel, since it is parallel to a direction of interest. To make it a vector quantity, we place that scalar magnitude f parallel on the unit vector. The perpendicular vector component is then the difference between the original vector f and f parallel. The dot product thereby enables us to resolve any vector in 3 dimensions into components parallel and perpendicular to a direction defined by a unit vector u without having to see the orientation of the plane defined by the 2 vectors. This movie summarizes the operations that lead us to defining f parallel and f perp. We define the unit vector from a relative position vector divided by its magnitude, and then define scalar magnitude f parallel as f dot u. We define vector f parallel as magnitude f parallel on u, and then define f perp as the difference between the original vector and f parallel vector. In effect, we back out the perpendicular component once we know the parallel component. Let's now return to our second example and the rotated coordinate system. The unit vector along the train tracks is defined in terms of the rotated coordinate system by u equals cosine 30 degrees in I minus sine of 30 degrees in j. The position vector from B prime to A prime is defined as r B prime A prime is r A prime minus r B prime is 11I minus 10j minus 2k feet. The magnitude of r B prime A prime can be found from the square root of the sum of the squares of those components and turns out to be 15 feet. The force carried by the chain can therefore be written as the tension on the unit vector from B prime to A prime, and that's 3,000 pounds on a vector 11 over 15I minus 10 over 15j minus 2 over 15k. And that turns out to be equal to 2,200 in I minus 2,000 in j minus 400k pounds. The force component along the railroad tracks is therefore F parallel equals F B prime A prime dotted into U. And making use of the Cartesian components, we have 2,200 cosine 30 degrees plus minus 2,000 times minus sine 30 degrees. And that number turns out to be equal to 2,905 pounds.